Okay, so we are ready to, I think, finish up Chapter 5 today. And Chapter 5 is, the last part of Chapter 5 is all about residual analysis, detecting outliers, all those kinds of things. We've already done a lot of that. Last time we did model selection with forward selection, backward selection, stepwise selection, and then the Mallow CP and all that kind of stuff, right? And so then once you pick a model, you have to then go through your diagnostic procedures to see, okay, now is that model acceptable? We've talked about collinearity and how to assess that. So that's part of the diagnosis of a model. The next thing that we need to talk about is detection of outliers. So that's what section 5.4 is all about, detecting outliers. And we'll have several ways to do this. But to motivate it, let's look at some data on height and shoe size. And you remember our really tall guy? Yeah, the size 22 shoe. And the, let me just do a proc print of it real quick. Or a G plot, actually.
What does a G plot stand for?
Graphics plot. Right? So here's a plot of that data. This is just one semester's worth of data the semester that he was in the class. And you see that you have a size 22 shoe and a height of 91 inches. So we don't need any fancy schmancy statistics to help us detect that outlier. As long as we look at our data, we can, whoa, look, there's an outlier in this data. But I want to use it because we know it's an outlier. Let's see what it does to all these statistics that they're going to teach us about in this section. Okay? The question is, definitely it's an outlier, but is it an influential outlier? And what does that term mean? Influential.
Well, if it's following the trend of the data, it's fine. But if it's if he's 50 inches and had 22 shoe,
that's right. If he was 50 inches tall, so his point was down here, what would that do to the regression line? It would pull it down. It wouldn't go all the way to this point, but it would definitely decrease the slope a lot from what you see here, right? So influential means that two things have to be true. One, it has to be extreme in the x direction, right? So extreme in value basically means it's sitting at one end of the teeter-totter, right? That's extreme in the x direction. Now, if you got a multiple regression model and you got 5 x variables, it means extreme in at least one of those x variables. But often what you'll find is an outlier that has really big feet and is really tall also is very heavy. So maybe if you have weight as an x variable, there'll be an outlier in that variable also. So they'll end up being extreme in all of their x values.
It just needs to be in one.
Right. To be influential, it has to be extreme in at least is a good way to say it. And then second thing, does not follow of other points. And when I say other points, I guess what I really should say is follow the trend of most of the points. Because you can have more than one outlier. Right? But you get the point. Does not follow the trend of the other points. Now what do you think about this guy? You think he'll turn out to be influential? It seems to pretty well follow the trend. So if you look at this cloud of points, it's a little disturbing to me that the line doesn't seem to go through, doesn't follow that cloud of points. But the thing you can't see from this, since the data are very discrete, right? Shoe sizes are only in half unit increments, and height is to the nearest inch. There's a lot of repeats. So what you can't see from this is that these points may be relatively few and these may be really heavy. So it's pulling the line down a little bit there, right? But just as an eyeball test to test for influential point, you can fit the model with that point in and fit it with that point out and see how things change. So this next G-plot says where height less than 90, because I know he was 91. So if I say less than 90, that's going to catch everybody but him, right? And I used all of the same axes, order, and all that stuff. You don't have to know how to program this, but just in case you're interested, that's going to produce the same exact plot, only not have that guy in it, right? So now I use animation. Page up. Oh gosh, it doesn't work. What I want is, I want it to move exactly so it looks like a slide changing. This is not going to show exactly what I want to show, but there's with the point.
The endpoints like at 87.
Okay, good. Yeah, look at where it hits the axis up there. It's at about 87, and the intercept here is at about 58, a little above 58. Right? Then I scroll down, take him out. But so what do? It decreased a little bit. So he's got some influence. It's not dramatic, right? But if we done what Taylor said and inserted that was height of 50, or even an average height of around 70, and made that 22 shoe have a height of 70, it would pull that line down a lot from where it is without him in there, right? So that's a measure of influence. Okay, so we have several measures of influence, statistics that we'll compute. One of them you're already pretty familiar with, and that's called the leverage, right? Also named, what do we also call that? The distance and the hat value. It has three names. So the distance for a point means the distance from the centroid, right? So this is only two-dimensional, so the centroid is the center of that cloud of points. So leverage equal distance equal hat value is a measure of identifying outliers. It doesn't necessarily measure the influence that the point has on the regression coefficients. If it's influential, it will change the slope. It will change the intercept, right? Those are the regression coefficients, or the regression parameters. The leverage only really measures how far it is from the centroid of the cloud of points. But it is helpful to pick off what it helps you pick off outliers. You'll need other things to determine if that outlier is also influential, right? But outliers can cause problems even if they're not overly influential. For instance, one thing that an outlier will do, remember that you have measures of variability, so standard errors on parameters and confidence intervals and all those things depend on the variability. Well, if you got a really extreme outlier, it's going to inflate your variability a little bit. So you won't get as tight of confidence intervals. You won't have as much power to detect differences from zero in parameter estimates and all that. Okay? So you've learned that the hat value is the diagonal element of the hat matrix that goes along with that particular x variable, x value. So that subject, right? What is the hat matrix? Oh, no, that's the distance value. So that's how you get the diagonals of the hat matrix, is you put the x0 is the vector for that one observation, right? Yeah. So the whole matrix is actually not x prime first. It's x and then x prime x inverse x prime. And they call it the hat matrix because if you take this thing and you multiply by y, you get y hat. It puts the hat on y, right? Because the beta vector is tangled up in there, right? So the diagonals. So let's see. Let's call this h. The diagonals of h are the leverages. And that's what Peyton was saying. That's a vector x0, and our book puts the prime here, which is different. I don't like that because I can never remember. That makes it so I can't remember which is which. But since I have it in my notes, we're okay. Right? So this is leverage for individual with x values in that vector. And remember, it's basically you take that person's row. So if they're the fourth person down in the X matrix, then you take all of their X values and you form a vector out of them, right? And you take the transpose of that times the X prime X inverse matrix times that vector, and you get the diagonal elements of this. Right? So SAS will produce those and give us values. So how do we know when we look at the hat values whether it's a big number or not? Right? We need some kind of a cutoff rule for when the hat value is big. So you can show, and I won't prove it, but you can show that the sum of all of the hats, and I'll call them HIIs, that's the notation we used before for these hat values, the individual values. So this is HII, so the ith diagonal element of the hat matrix, right? So that's the leverage that corresponds to that combination of x's. Right, so the sum of all of the HIs is equal to k plus 1. Oh, I got so many things I got to keep straight. What is k? Number of variables in the model. Right? So the sum of the HIs will always be k plus 1, which means the mean of HIs is k plus 1 divided by n, sample size. Right?
Real quick question. In the case of reduced versus complete models, does K change between the reduced and complete models because we're removing certain dummy variables?
Yes, if you did a complete model and a reduced model, but that's really not the discussion here. We're just trying to find individuals who are influential or are outliers in the model that we've chosen. We've already selected our model now, so we're past that reduced model, complete model, is one model better than the other. We've already made that decision. Okay? But you're right, it would change if we did. Well, if the mean, and we'll call that H bar, if the mean of all of the hat values is a known quantity that we can compute pretty easily, then we'll decide if a particular individual's hat value is extreme by seeing, is it a lot bigger than the mean? Right? So the leverages are go ahead.
Where are the 2 lines versus?
It's just because it's from the hat matrix, so matrices have have 2 subscripts, the ith row and the jth column, but to denote that it's a diagonal, this is a quick way that authors, not just this book, but most stats books, if you see a double subscript like that, and it's II, then you say, oh, we're talking about the diagonal element off a matrix. And then you just have to, okay, what matrix and all that, right? But it's saying it's the ith row and the ith column, it's a diagonal element. That's why there's 2 subscripts. That's a good question. Right? So we will flag HIIs that are greater than 2 H bar. Some books say 3 H bar. I'm never one for a strict cutoff, right? Because that's an arbitrary value that somebody threw out there and said, well, this seems to work pretty well. So just make a decision based on, well, it's greater than 2, but it's not quite 3, so it's sort of, yeah, it's probably an outlier. If it's greater than 3, then definitely it's an outlier, right? So let's see what this guy is. When I run the regression model, here's how you do that to get the, let's see, I don't want that one, I want this one up here. Okay, so proc reg, then I called the data set males, I subset it out, I put a title in there. Right now I have a statement where height is less than 90, because I would run with and without this guy in it, but that's commented out. Right, so the asterisk at the beginning comments it out. So model height equals shoe size, and then options. R for residuals, print the residuals. P for, what did you say? No, they're not. It's for predicted. And you can actually you can type out the whole word predicted, or you can put a P. So that lets you have that abbreviation. It does not do the same thing with residual. If you type out the whole word residual and say, I don't know what that word means, you have to use an R. So SAS is one of those software packages that was written by committee, so sometimes things don't seem to correspond. And then the word influence. The word influence is going to produce a whole host of these influence statistics, things that try to see, does this particular observation have influence on the model? Right? So I'm going to run that, and I'm going to go ahead and just run it as is with the new version and all the graphics and all that stuff. But I may come back and turn those off and rerun it if it's more than we can handle, if it makes it hard to find stuff. Right? So it's running. We're going to get residual plots out of this. We're going to get normal probability plots, and we're going to get all kinds of stuff. And we want to look at them all. I had a plot statement in my regression. I didn't need it because it was going to give me this anyway. But it's left over, so it's in there. So that's That's very similar to the one I showed a minute ago with the proc G plot, only it puts some more information. It tells me up there what the regression equation is, and then what my R square was and all that. So I got n equal 127. Right? So what is H bar? H bar is, yeah, how many variables do I have in the model? Just one. So K is a 1. So 2 over N. So 2 over 127. And what is that on your calculator? I actually wrote it in my notes, I think.
0.01575.
Okay, 0.01575. Okay, so that's H bar. So 2 H bar, say, times 2.
0.0315.
All right, so anything that's bigger than that for a hat value, we're going to think is a potential outlier. So I'm going to start paging up. There's the fit plot. I like this fit plot for this particular data because you see the usual flare in the confidence bands. But because we have such an extreme outlier out there, it goes further and you really see that flare. And you see a lot more flare off that end than this end because the centroid's down in here. Right? So you get a lot of flare there. There's also flare in the dotted lines. What are the dotted lines? Prediction intervals. But it's just harder to see because they're so wide anyway. Right? The flare isn't so dramatic for them. But what do you notice about the prediction intervals and our guy? Yeah, he's in there, but he's barely in there. There are others that aren't in there, right? So these are also outliers, but they're not outliers in the X direction. They're only outliers in the Y direction. For their given shoe size, they're way taller than you would expect. Okay, so residual plot. Anything annoy you?
There's that one guy that's at the top of the chart.
That one?
Yeah.
Okay, and that's going to be the same one we saw that was way outside the prediction interval, right? A much bigger residual than expected. The residual for this guy is not really any bigger than you would expect. Kind of on the cusp of it. But other than that, any patterns or things that seem to violate? No, everything seems okay. Got a couple outliers. Okay, there's a histogram of the residuals. You see a little bit of a tail off on the right side. Look at the QQ plot, the quantile plot. The quantile plot is here. You see some skewness, right? So you got a little bit of skewness to the residuals, but you also got a little bit off of this end, right? So it's kind of interesting, but nothing that's too worrisome. If this is our one guy. Actually, who is that guy? Do you know?
Is it the same guy that was the really high residual?
Yeah, it's not our 91-inch tall guy. It's the one with the biggest residual because this is my residual axis. So the biggest residual, and that was the guy that was outside that prediction interval. So a little bit bigger than you would expect for that residual. Nothing else is too concerning. Okay, so we have a plot here called leverage. And these are the leverage values versus the studentized residual. That's one of the ones we're going to learn today, studentized residual. But it's the residual, but it's been standardized. So we've got a high leverage value. Let's see if that's our guy. These are plots that I would just soon turn these off because they don't mean a whole lot to me. But well, actually, these aren't too bad. Cook's D we're going to talk about here in a minute. Let's find the one that is hat value. Student I guess they don't do a plot for hat values. But SAS is the new version of SAS here. I've not seen this before. Is highlighting the ones that seem to be ones you want to look at. So it's flagging them. That's the word we use. It's flagging. You might want to check that. Right. And there was another one. Yeah, right there. What does that arrow mean? Yeah, I'm just guessing because this is new to me too. This is a new version of SAS, but it's meaning it's further out even than that. We just ran out of room, so it's out there, right? And that is studentized residual, and so this would be a value of 1 would be 1 standard error out, 2 standard errors. You get beyond 2 and you start to be concerned. Or that's 3, right? I don't know if you can see it, but there's a faint line right there. Right? So it's actual. It lists its value there, right? So it's 3.88. So it's a very big residual there. But here's what I want to look at. So I've got to get to the top so I know what the columns are. Right here it says hat diagonal. Right? I need to leave this here so that when I walk over there it doesn't come off the screen. So the hat diagonal, we're going to be concerned if anything gets above 0.02. Let's go ahead and do 3 also. So multiply 0.15 by 3 and you get about 0.0472. Okay, so anything above that we would definitely want to take a look at. 0.0315, we've got 2 right off the bat that are above that. Right? None of the rest on this page. The dependent variable was a 67-inch tall. I guess I was thinking it also showed their shoe size on this, but it doesn't. You can make it do that, but I think in order to do it, you have to save this as a data set, and then it'll have all of the original variables in the data set plus all these new ones. And you tell it which of these you want. Then you could print the shoe size out with it, which is helpful, I think, to see, okay, they were 67 inches tall, but they had a shoe of, that's why their hat diagonal is so big. Now we have to go to the plot, see who had 67 figured out. So relatively medium people, 67 inches is 5'7", 5'8", so they must have had odd-sized shoes. In fact, that one really extreme outlier, weren't they down around 67 inches tall, something like that? I don't know, we can go back and look in a minute. But. So let me keep scrolling down here. Oh, I remember now. I was going, why are these in order?
Did you sort them?
I did. I sorted before I ran that project. I sorted by shoe size, I think. So they're not sorted by height, but they sort of are because they're sorted by shoe size. So, okay. But these numbers are all. Remember, the hat value doesn't deal with the y variable. It only deals with the x variables. Right? There's no y in this whole thing. Matrix operation. There's no y vector. So it only is a function of shoe size. So every time they have the same size shoe, you're getting exactly the same. Okay? Now here's my 91-inch tall guy at the very bottom. What'd you say? Yeah. So this guy, which column is my hat? That one, right? So the hat value is So this guy's HII is 0.2662. So we're going to get concerned if it gets above 2 H bar, real concerned if it gets above this, and he's way beyond that. He's 6 times that big. Right? So very, very big leverage value for that person. Okay, so that's the first measure, a leverage value or a hack value. So the next one we'll talk about.
So and he's has a lot of leverage though because he's the only one out there, right? Because if you have like a data set of 1 million people, you may have people that are 7 foot tall to kind of offset it.
I was just going to ask that too. What if you have a group that using influencers? I'm just thinking about credit unions that have fraud. Their metrics are going to be so much different. And then credit unions that are reporting first. If you know that, would you just try to put it as a variable and do like a dummy variable with the 2 models, or?
If you had credit unions that were committing fraud,
Yeah.
so they would show up as an outlier in some of the variables.
Yeah, there's a lot of them. There's like a group of them, and
Okay.
it's not like just one.
Oh, I see what you're saying. So this guy is one guy,
Right.
so he gets flagged as being leverage. Well, leverage value does not depend on sample size, right? The mean leverage does, right? But just the leverage value for a particular individual doesn't depend on sample size. But all of those that are out there in a cluster together, they would all have similar leverage values, right? And they should all be flagged. The sample size will affect the mean, but it will also affect them. But relative to that 2 times H bar or 3, they would still all kind of go together. So yeah, that'd be a way to flag them, I think. Okay, so the next one is called the studentized residual. And there is some discrepancy between our book and what SAS calls things. So I'm going to try my best to remember those discrepancies. And other books define things slightly different. I call this R sub I. R sub I equal student is equal to E sub I divided by standard error of E sub I. Where E sub I is the sample estimate of epsilon sub I. So this is the observed residual, not the population residual for this person, because we don't know what the true population regression line is, so we can't compute the actual population residual epsilon I, but this is our estimate of that. And then we have a standard error of the residual. And we did standard error residuals way back when. That's basically your root mean squared error. I wish I had a way to keep the columns so we could read them and put our 91-inch tall guy on it. But if you look at standard error of the residual, right there, right? So which column is that? 1, 2, 3, 4, 5th column over. And then let's go down to this guy. His standard error is 1.825. Okay, 1.825. And then we need to know his residual before we standardize. Did anybody happen to... I wasn't smart enough to look at both columns I needed. So I got to go back up. Residual. So it's the one right next to it, to the left. Whoops, wrong. So 4.2851. Everybody see that? 4.2851. Do that, and you get 2.348. Okay? Now, do you see that number on this row? Right there. The one just to the right. Right? So, if I page up, that's the student residual. SAS calls that the student residual. Right? So, student. Where's the word student? Why is that used? Yeah, student's T distribution. So it's studentized is the way they say that. It's a studentized residual. So it's been standardized, but standardized according to the T distribution, not the Z distribution. Right? And it's because we have to estimate this standard error from our sample. We don't have a known population. Okay? So then we can compute deleted residuals. And it's the residual for a particular individual when that individual was not used to fit the model. Right? So I take them out, I get the parameter estimates, then I see the predicted value from that model of what I think he should be, his height, and then I see the residual from that. So it's not the observed residual, which was from a model that had him in it. It's the deleted residual. Okay? So we denote that with yi minus yi hat and put the little I in parentheses. So that means ith observation deleted. Okay? The book calls this the press statistic, but I really think that's just wrong. SAS uses the word press in all caps because it stands for something. Predicted residual error sum of squares. Right? SAS uses this for something completely different. Right? It's the sum. It's error sum of squares. And our author's using that word to be an error for just one individual. Right? So I don't like the fact that he calls it press, but you need to know when you're reading the book that, oh, he's talking about what we call the studentized residual and what SAS calls studentized.
Wait, we need deleted residual?
Right. I'm sorry. I pointed up too far. You won't hear me call it this. I'll call it the deleted residual. Right? Not the studentized. But there is a studentized deleted residual. So guess what that is? Well, it sounds like the studentized deleted residual would take the deleted residual and standardize it, right? But it's actually more complicated than that. And this is denoted with R sub I in parentheses. Right? So studentized is R with no parentheses around the I. Deleted studentized is R with the parentheses. And this is computed as y hat I, and then S parentheses I, square root of 1 minus the hat value. Okay, now we got to compute this. And this is what SAS calls R student. So let's see, our student is, let me count, 1, 2, 3, 4, 5, 6, 7, 8, 8th column over. Uh-oh, it locked up. Okay, there we go. So now count 8 columns. 1, 2, 3, 4, 5, 6, 7, 8. Right? So our student equals 2.3915. So it's the predicted value that's not right. This formula is not right. What I have is, this should be yi minus y hat. I was thinking, why would you take the predicted value to get a residual? But it should be a residual. So this is just EI. Right? And then, what the heck is that? You should start to get the pattern in subscripts and all. What does the parentheses around the I mean? Deleted. And then what's S? That's the standard deviation from the model, so that's root mean squared error. So I need to run the model without them in it, get the root mean squared error, and that number goes right here. Right? So let's start building this thing. On the top, I need his EI, which we got before. Just raw residual, not deleted or anything. 4.2851. Now,
you said the root mean squared error of the model with the delete,
right,
with the one we don't want.
Yeah. So in these statistics, parentheses around the subscript means that that observation has been deleted to compute this statistic. And I find it interesting that it's the studentized deleted residual does not use the deleted residual up here. It uses the regular old residual, right? I don't understand. I've never understood why do they not do that? But it must have, this must have properties that are easier to deal with or something. I don't know, but so let's run that model with that guy deleted. So now I just need to uncomment this where statement and say where it's not equal. And then I don't want all the other stuff. So I'm going to say ODS graphics off. And then I'm going to comment out the plot statement. And I'm going to comment out all of those options. Just remind me to turn them back on if we want to run something else. So this now has how many? Oh, it's up there. 126, right? So one guy's missing. That's our 91-inch tall guy is missing. So now I got root mean squared error. That's my S sub parentheses I. Is this root mean squared error. So that is 2.09181. And then the square root of the hat value. And notice there's no parentheses around those i's. So that's just that guy's hat value. Not deleted, anything like that. So that's 1 minus, and it's written on the board over there. What is his hat value? Okay, so now compute that.
How many were in the model before that? We just took out that. So is it just, you have to take out that one for each root mean square? You can't take out like 5 and then find the root mean square error?
That's right.
I'm just looking for that.
These are one at a time,
Okay.
right? Deleted residuals are one at a time, everybody else in. Now, there's not, what you're suggesting has definite merit, but there just isn't, there isn't software that's going to do it automatically for you, right? So what value did you end up with?
2.792.
That's not what I got in my notes. That's what I got. 2.3914.
I forgot to take the square root, that's why.
Okay. Okay, and that matches almost what SAS calls our student. And it's not matching at the 4th decimal place just by round off error. If we had, they only gave us 4 places on our hat value. If we could get it to print more, and you can, then we would have been more accurate and we'd have matched that exactly, right? So that's how SAS is computing the R student, which he calls studentized deleted residuals. Okay, so now we've got a number 2.39. Is that big? How do you decide if it's big enough and should be flagged? Well, if it's studentized, it must have what distribution? T. So you get a critical value from a T and see if it's bigger than that critical value. So what is the critical value of the T? Well, in order to get a critical value, you need to know degrees of freedom. So the studentized residuals, both of them, we have a studentized deleted and a non-deleted one. The studentized residuals are big if greater than the T critical value with N minus K plus 2 degrees of freedom. Actually, that's I made it sound like both of them are that. This should look a little bit odd to you, which has made me realize, oh, I should have said this before. Why is it K plus 2? Because I took one out, right? So I'm subtracting one more off. We're used to N minus K plus 1, right? So this is the one for deleted residual. So this one is deleted. The non-deleted, right? I don't know what to call it, but just the RI, let's just do it that way. RI, it's with N minus K plus 1 degrees of freedom. Now, if you have a reasonably big sample size, like this one, 127 observations, degree of freedom off by 1, you're not going to see any real difference in that t-critical value. And most of the time, it's going to be a number that's around 2. So if it gets bigger than 2, then you start to say, ooh, that one's potentially big. This one's 2.39. Right? So to get a t-critical value, there's one thing missing here. You need an alpha level, right? So how many standard errors do you want? So typically we go 95% confidence, so alpha 0.05. T-critical then would have 0.25 off of each tail, and you'd call that your critical value for this. It's a matter of personal preference, but as we saw, SAS draws those pictures, and it's going to flag the ones that get out about beyond 2, is what it does. Okay, so let's scroll back up to that plot. This is studentized. I can't highlight it, but it's covered up by words. This is our guy, 238. That's the number we have over there for the studentized residual. And then it's not our student, but here's a faint line and a faint line, and then 3. So this studentized residual greater than or equal to 3 is colored red. This one didn't make it to 3. It's at 2.348. So it's one you would want to look at, but it's not going to get flagged as definite, right? So basically they're saying 3 standard errors, that's way out there. So they kind of dispense with the whole t-critical thing and just say 1, 2, or 3. Is it bigger than that? Right? Then it has prob less than or equal to 0.024. That's just the probability that goes along with being more than 3 standard errors away. So if you do a p-value instead of a critical value, that's the cutoff. Okay, now let's talk about Cook's D. I guess we're done with all this. Cook's D gets at the idea of influential by looking at how do the regression coefficients change when that person is deleted. Right? It's a kind of a deleted thing again, but it's interesting how the algebra works out. It doesn't seem like that's happening. But I had to be convinced in graduate school that it was indeed happening. No, it's more complicated proof than what I'm willing to go through. But it's called Cook's distance. And this is not Sarah Cook from our math department. It's a different Cook. Not that she's not capable of it. It's just before her time. So Cook's distance we label as capital D sub I. And it's a measure of the distance between the parameter estimates with I and without I. Okay? So measure of distance. So everybody's happy with leverage as a measure of distance. This is point, and we measure the distance from the other x variables. Well, think about they call it the parameter space. Right? So you have this, in this case we've got 2 parameters, an intercept and a slope. So I've got a 2-dimensional space of where parameters could fall. So okay, where are the parameters in that? If I have beta 0 on this axis, beta 1 on this axis, then here's our particular study. Now if I take that guy out, it moves to here. It's the distance between those points. Right? Measure of distance. I don't want the word from, I want between. Distance between the parameter estimates. When ith observation is in and when it's out. And algebraically, it is a pretty nasty proof to get there, but algebraically, what they showed, what Cook showed, was that this is equal to 1 over k plus 1 times the hat value over 1 minus the hat value times Ri squared. And remember, Ri is what I erased it unfortunately, but Ri was what we called the studentized residual. Okay? So I have no insight or intuition as to why that formula works, but it does. It gives you this measure of distance. So here's how, let's plug in the numbers. Our model, k is 1, so this is 1 over 2, so that's 1/2. Our hat value is 0.2662, so that over 1 minus that. And then our studentized residual we computed a minute ago, and we got 2.348. And when you compute that, you get, and I'm going to write this out like this because I found it interesting. Right? That is pretty much 1. Right? And SAS calls it 1. Right? So to that many decimal places, it is a 1. And the reason I found it interesting that it was just a tiniest little tick below 1 is that a lot of textbooks say flag it if it's greater than 1. So flag if greater than 1.
And you keep trying to get rid of this guy and he just wants to stay.
Yep. He snuck in there. He just barely snuck in there. But our author makes it more complicated than that. So he's definitely in according to our author. Our author says, so our book says, if di less than f sub 0.80, and that's our book's notation for this, but this means this is right tail probability. So it's an F critical value from an F distribution with 80% in the right tail. So what percentile would that be? If 80 is in the right tail, it would be 20 in the left tail, so it's 20th percentile. So I'm going to write that over here. 20th percentile of F distribution. And, with k plus 1 and n minus k plus 1 degrees of freedom. Remember, with an F, you have numerator degrees of freedom and denominator degrees of freedom.
So the lower.
Okay? So if this is true, if it's less than the 20th percentile of an F distribution, then no worries. This person's not influential. So if that, I'll say no worries. If it's greater than the 50th percentile, then influential. Flag it. Oh shoot, my battery went dead.
So
Yep.
Why is K 1 in this case?
Because I only have one X variable in the model.
Got it, okay.
Yep. Now, notice that these two numbers are different. So it's not a cutoff. Below this you're okay, above this you're not okay. There's a gray area in between. Right? So if you're below the 20th percentile, then no worries at all. If you're above the 50th percentile, then it's definitely influential. In between the 20th and the 50th percentile is questionable. Examine it, but it's not dramatic. So
Can you plug that into the F CDO?
you plug it. You get these F critical values from an F inverse, which you may not have on your calculator. I programmed into my TI-84 an F inverse function. Do you have F inverse? Some of them do. The really new ones, the Inspire is probably going to have it. But
Yeah, mine doesn't have it, so it doesn't have that.
but short of programming that into your calculator, you can get it from an F table, right? But on a test, I don't think I would require you to know how to get those. I would say, given that the 20th percentile is this and the 50th percentile is this, what do you think about this observation? Right. So if we did look them up, this 20th percentile is 0.22 and this 50th percentile is 0.70. So now what about our guy? He's out. Because he's a 1. Right? So 0.7 is now the cutoff. So our author is more liberal. This would be more conservative to only flag if it's bigger than a 1. You're not going to flag near as many observations. And I tend to want to flag as much as possible because I can always make the decision, no, I want to go ahead and keep them, but I want to at least know what I should be looking at. Right? So that's what these tools are for. They're just pointing out to you, here's one you ought to examine. Is there something wrong with this data? Is he really 91 inches tall, or is that a typo?
So
right?
this is just telling you that this is out of the norm. It's not really
Right.
telling you shouldn't be written.
Right. It's not. No procedure can ever tell you that. It does not tell you that you should delete this. It says you might want to think about deleting this one, right? Because if you can't fix it, if it is a typo, you can't fix it, then it's gone. But if it's a real value, like this one is a real guy that really was that tall and he really had a 22-inch shoe, then I said, well, I probably don't want to take it out because I'm trying to get a model that fits all males. He's part of everybody, right? So. Okay, so now let's go back into the list of values. SAS is helping us to flag things, so they flagged this one for us, right? So, we got a big Cook's D. So that's saying, even though our eyeball test said, the line didn't seem to move that much, it moved enough that it got flagged as moving the parameters. It changed the slope and the intercept enough that Cook's D picks it up. It's borderline, but it picks it up. If I start scrolling back up, then, I just noticed, look at this one. That's a 0.04 Cook's D, but SAS highlighted it, and it said, down here it says, Cook's D greater than or equal to 4 over N. Now, I've not seen that in a book before, so that's something maybe new that's been published since, but 4 over N, so 4 over 127 is 0.031, so they're flagging anybody that's above 0.031. So I don't know where that comes from. I don't have a justification for 4 over n, but yeah, Peyton.
For your notes on the bottom, it says VI less than F of 0.8 and then VI greater than F of 0.5.
Right.
Are those supposed to be going the same way? Because what if you have an F of 0.6 in that situation? It's a gray area.
You stepped out of the room, didn't you?
Yeah.
Don't do that.
Okay.
Just kidding. There's a gray area in between.
Okay.
So less than this one, you're fine. Greater than this one, there's a problem. But in between the two, it's kind of close. We're not sure. It's a gray area. So usually it is a cutoff, like you're saying. But in this case, there's room in between. Okay, so using our cutoff of 0.7 that our author uses for definitely a problem, do you see any others? There's a 0.06. No, it's 0.06, not 0.6. Yeah, it had to be 0.7 to be. So SAS's new thing of 4 over n, I kind of like it because I've never been happy with just a blanket 1. It's bigger than 1, and that always bothered me a little bit. This, I didn't have any great justification for why these F critical values, but this thing, when you square a studentized residual, you're getting an F statistic when you do this. But I don't know.
So that 0.999 is an F statistic.
Yeah.
Okay, that's what.
Yeah. It has an F distribution. It's not readily apparent there, but it's part of that algebraic proof that shows it gets there. It is.
So that's why you can compare them directly to the F.
Right. So. Okay, I've got 5 minutes left, and I've finished chapter 5 now. That's the last one of those that we're going to do. So I did not finish it before I came today, but I have almost finished your big project for the semester, your sheet, to get you going on that, right? The one thing that I didn't realize till I was making that out, we never went back and did the rest of the Da Vinci data, right? The pooled data for Da Vinci. So I think I'm going to make that part of this week's homework, right? So I'll take out some of the book problems, and I'll just say use the pooled Da Vinci data and fit a multiple regression, look for collinearity, those kind of things, right? Because some of those variables should be kind of collinear. We'll see how much, right? So we'll do a little bit of that, do some Cook's D on there, where do you have any observations that are influential? So run these diagnostics on that data, right? So that's how we'll get through, and we won't make a project out of it. But then your project that you're going to do, I'm going to let you, like we did in time series, you can go out and find a data set that you're interested in and run some kind of analysis on that. Or if you don't come up with one, then I have the 2007 version of the MEPS data. And MEPS stands for, I got to remember, Medical Expenditure something survey. I think public. Medical expenditure public. It's not public. I forget what it is, but it's in the document I've already typed up. But basically it's claims data from health insurance, right? So it's got millions of observations in this data set. And so it's like every time somebody submits a claim to Medicare or whatever, it goes in the MEPS data. So it's something that actuaries use a lot, is data like that, to mine the data, look for subgroups that predict, big claims, subgroups that predict death, all those kinds of things. So, you won't be fully able to analyze that data until we get through logistic regression, which we will start Monday, right? So logistic regression will start Monday, but you should already start the process of looking for a data set to work with. If you want to work with the MEPS data, I didn't update to the last. It's always a few years behind, so probably the last one out there now is like 2012, because it takes them a long time to process this data and get it ready for public use. But U.S. Census Bureau, Bureau of Labor Statistics, websites like that have a lot of free downloadable data with huge data sets and lots of variables. So if you want to try your own, go for it. If you want to do the MEPS, then you can use that. Right? I also have, but Peyton's not allowed to do it, the baseball salary data. But you've already done that. Well, you did a project.
I don't recall ever doing a baseball salary.
Yeah, right. And you were in, didn't we do that? Weren't you guys in 343 together?
I did. We did. Are you talking about the 2001 or?
No, this is the 2011 data.
All right, I did that one, and then for time series, I actually did a baseball salary.
Yeah, I remember that.
Straight or highest players, and.
But that wasn't off my data. That was off of So if anybody else is interested in,
Can I do that?
you got what?
I have 2015 baseball statistical data.
Well, yeah, we might talk about that as long as you give that data to me so that I can use it in later classes. But
You're always on the hunt for data.
yeah, that's right. That's right.
I really wish I could give you some of mine because it's so fascinating.
Yeah, and I would love to get some real data like that from the banking industry.
They scare you.
All right, we will see you on Monday, and I will have this document out there and your homework document out there sometime in the very near future. So it probably won't be this afternoon because I know what the rest of my afternoon is like, but see you then.